Math 154 students, today we're going to be talking about putting numbers in perspective. Specifically, we want to talk about scientific notation, which is extremely useful when we're talking about very large or very small numbers. We're going to talk about putting numbers in perspective through estimation, comparisons and scaling, as well as applying these skills of estimation and perspective to real-world cases. So we often hear numbers in the millions, billions, trillions in contexts such as government spending, memory storage, but it's hard to really understand what these large numbers mean. So let's look at several techniques for putting very large or very small numbers into perspective and giving them real meaning. The first thing we're going to look at is scientific notation. You've probably seen scientific notation before, maybe it's been a while, but it's a format to express a number that is either very large or very small. We're going to express that number between 1 and 10 multiplied by a power of 10. We've got to be careful when we're looking at numbers expressed in scientific notation, because if we see something like 10 to the 80th, we might not quite have an understanding of how large that number is. We might think it's really not all that big because it's just expressed in 4 digits here, 10 to the 80th. But actually, that number is larger than the total number of atoms in the known universe. So it is an extremely large number. Scientific notation will be in the form a times 10 to the r, where a is between 1 and 10, and r is an integer. The integers are whole numbers that you count with, plus 0 plus the negative numbers. So just a reminder on that one. Here's the example of the integers. -3, -2, -1, 0, 1, 2, 3. And the ... dots represent that we keep going in either direction. When we convert to scientific notation, we want to keep moving the decimal point until we have a number greater than or equal to 1 and less than 10. There should only be one digit in front of the decimal point. Notice there I said in front of the decimal point, not after. The number of places we move the decimal point will correspond to the exponent on the power of 10. So if we have a large number that we want to write in scientific notation, numbers greater than 10, we're going to move the decimal until we have one digit in front of the decimal point, count how many places you moved the decimal, and now write it in scientific notation. So we're going to have that number multiplied by 10 to the r, where r is the number of places you moved. So for example, we have this number 2 trillion. We move the decimal from where it started. Remember that there's always a decimal at the end of the number. It's not usually written, but we know that if there is no decimal already in the number, we can write one at the end. So then we moved it back 9 times to get to the 2. We know that we needed to move it back all the way to be after the 2 because we need the first number to be between 1 and 10. So if I had moved it back and gotten 20, I would have said, wait, 20 is not between 1 and 10. So I need to keep going. So since we moved it 9 times, the 9 is going to be our exponent on the 10. So our scientific notation is 2 times 10 to the 9. This 10 should always be a 10. If we're converting small numbers into scientific notation, numbers that are less than 1, we're moving the decimal to the right until we have, again, one digit in front of the decimal point. Count how many places you move the decimal. And now our scientific notation will be 10 to the negative r. So since we're moving the decimal to the right, it's actually going to be negative r. So this time I moved the decimal again 9 times, but this time I moved it to the right. So it's 2 times 10 to the negative 9. Again, the 10 didn't change. It's always going to be 10 there. So let's go ahead and write the following numbers in standard form. They are written in scientific notation, but I want to write them in standard form. The first one is 7.53 times 10 to the negative 10. So I know that if my exponent is negative, I'm looking at a really, really small number. Now, for small numbers, when I wanted to write it in scientific notation, I move the decimal to the right. But this time I want to write the standard form. So I'm actually going to move the decimal to the left. I'm going to go ahead and write the 7.53 over here because I know I'm going to have zeros in front of it because I have a small number. I need to move the decimal to the left 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now, anywhere that I have that empty hump, I need to put a 0 in. So my final answer, 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 5, 3. The mass of one of Jupiter's moons, and this should be an exponent, 16, 3.6 times 10 to the 16th. So I know that since I have a positive exponent, that means I'm moving the decimal to the right. I'm moving the decimal to the right 16 times. So 3.6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Anywhere that I drew a little hump, I need to fill in with a 0. All right, so that is 36 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 zeros on it. Now let's go ahead and write the numbers in scientific notation. The total spent on the 2020 federal budget was this huge number. So if I want to have the number between 1 and 10, I'm going to take my decimal, which would be after. I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You might be tempted to stop at the 5 because it's not a 0. But remember, our first number needs to be between 1 and 10. 65 is not between 1 and 10. 6.5 is between 1 and 10. And of course, now I forgot how many times I moved it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 6.5 times 10 to the 12. The diameter of a hydrogen nucleus is about a very, very, very small number of a meter. So let's move the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 1 times 10 to the negative 15. And if you forget which way do I get the negative, which way is it positive, just remember that if it has a negative exponent, it is a really, really small number. If it has a positive exponent, it is a very large number. So let's look at comparing some numbers with scientific notation. So the first one, 3.4 times 10 to the 5th, we are comparing to 4.8 times 10 to the 5th. So these are both times 10 to the 5th. So it's almost like it doesn't matter. They're going to have the same number of zeros after. So now I'm really just comparing 3.4 to 4.8. So 3.4 is less than 4.8. 7.9 times 10 to the 4th is what compared to 7.9 times 10 to the 6th? Well, now I've got 10 to the 4th and 10 to the 6th. The one with the 10 to the 6th is going to be larger. 5.2 times 10 to the 6th times compared to 5.2 times 10 to the negative 6th. Well, this one's got a positive exponent. This one's got a negative exponent. The one with the positive exponent is definitely going to be much bigger. Now we've got 8.3 times 10 to the negative 4th compared to 8.3 times 10 to the negative 3rd. So the number that has the one with the negative 4 is going to be smaller than the one with the negative 3, because negative 4 is less than negative 3. Or you can think of it as, with the negative 4, we're moving the decimal one more place to the left. 4.1 times 10 to the 8th compared to 1.2 times 10 to the 9th. Well, it doesn't matter that 4.1 is more than 1.2 because this one has another 0 on it because it's 10 to the 9th. So this one is still larger because it's got a whole nother 0 on it. If you ever had any confusion, you could certainly write these out. Example 4, which of the following is the greatest? So the greatest one is going to be the one with the largest exponent. So it would be letter B, 5.604 times 10 to the 9th. Since that one would have the greatest number of zeros after. Write the following in order from least to greatest. So let's start with the least. The least would be the one with the smallest exponent. Well, we've got two of those. We've got 10 to the 4th and 10 to the 4th. So now we have to compare the numbers in front. 4.08 is going to be less than 5.1. So 4.08 times 10 to the 4th would be the smallest. And then we have 5.1 times 10 to the 4th. And then the next one would be the one with 10 to the 5th, because 10 to the 5th is smaller than 10 to the 6th. So 1.23 times 10 to the 5th is less than 7.9 times 10 to the 6th. Letter B, the smallest number would be the one with the smallest exponent. Now we have some negative exponents. So remember, -4 is smaller than -3. So 7.3 times 10 to the -4 is less than 5.6 times 10 to the -3 is less than, now I'm comparing my positive exponents. 5 is going to be smaller than 7. So 9.01 times 10 to the 5th is less than 2.3 times 10 to the 7th. So hopefully you're noticing that what we're really focused on is what the exponent is. And then if the exponents are the same, then we look at the number in front. So let's determine which planet has the smallest diameter. The smallest diameter is going to have the smallest exponent. So we're between a 10 to the 3rd and a 10 to the 3rd, between Mercury and Mars. Since they are both 10 to the 3rd, then I'm going to look at the number in front. I've got 4.87 and 6.79. Well, 4.87 is smaller, so Mercury has the smallest diameter. Which is larger, an antibody cell or an influenza flu virus cell? So the antibody cell measures 1.2 times 10 to the -8. A flu virus cell is 1.3 times 10 to the -7. So both of them are very, very small, but the larger one would have the larger exponent. Remember that -7 is greater than -8. So the flu virus cell would be larger. Scientific notation can help us approximate answers without a calculator. So we can approximate the answer of 5,795 times 326 by rounding 5,795 to 6,000 and 326 to 300. So then we've got 6 times 10 to the 3rd. So that is just us writing 6,000 in scientific notation, because I would move the decimal 1, 2, 3 places. And then 300 should be 3 times 10 to the 2nd power, or 10 squared, because we would move the decimal 2 places. So when we have these two pieces of scientific notation multiplied together, what we're going to do is we're going to multiply the numbers. So 6 times 3 is 18. And then when we multiply exponents, we add them. So we get the 5 by doing 3 plus 2. So our approximation is 1,800,000. So let's go ahead and find the actual answer. 5,795 times 6,000. I get that my actual answer, not times 6,000, 5,795 times 326 is 1,889,170. So how do they compare? I mean, it's not exact, but it is very close. It's only 89,170 off, which, considering how large our number is, it's a decent approximation.